Hi, I'm Doug Black, Editor-in-Chief at Inside HPC, and today at SC21, we're talking with Phil Murphy. He's CEO of HPC interconnect company Cornelis Networks. Phil, welcome.
Thanks, Doug. I'm really excited to be here today.
Okay, great to be with you. So please just give us an overall kind of an introduction to Cornelis.
No, sure, absolutely. Cornelis Networks has a really deep heritage in high-performance computing interconnects. Me personally, I was working in a mainframe company back in the late 1990s, and became aware of the fact that Intel was trying to solve this problem that they had inside their servers with there was this parallel high-frequency bus called PCI-X, and they needed a way to improve that, and they created this technology called Next Generation I/O, which was this high-speed serial interface, aimed at solving that problem and maybe then expanding into the enterprise data center, replacing fiber channel or even Ethernet back in the day. And of course, the industry wasn't too excited to have Intel control the technology, so there was alternatives proposed like Next Generation I/O from IBM and others. And it was in this kind of world that I started my first company. And fortunately for me, these groups put their differences aside and created the Internet Band Trade Association, right in this time frame, which is the impetus I needed to get my first company off the ground and funded. And we decided to take a little bit of a different approach and say, this technology has really high bandwidth and very low latency. Let's take it to the high performance computing market instead of what everybody else was doing. And so I started a company called Silverstorm, and about a year later, there's another company in Mountain View called Pascal that was also started that was focused on high performance computing as well. And we call this the startup era. Okay, this is where this technology is mostly being driven by startups. And in 2006, though, QLogic Corporation out of Orange County, California, said, we're interested in expanding our product line and would like to bring you guys in. So they acquired us and they acquired Pascal and formed the Network Solutions division, where they were taking high performance computing interconnects to market. And so we did some great work there as well. We did some quad data rate InfiniBand products with our own ASICs and software platforms, across the board. And it was at this time frame that after that was out in the market, Intel contacted us and said, hey, we're doing a new processor type called, it eventually became called Xeon Phi, and it makes sense to integrate this technology into the Xeon Phi die itself. And so, we joined Intel. We did do a discrete version first to be able to prove the architecture as well as get ourselves established in the market. Unfortunately, though, Intel decided not to go forward with the Xeon Phi product line. And so this was an opportunity, right, to say, well, look, the reason you brought us in was to integrate this into a processor, but it doesn't really fit here anymore. We'd like to take it back out. And so that's where we came from. Okay. We were able to basically acquire the high performance interconnect division from Intel. And I forgot to mention that previously Intel had also acquired a team and some technology from Cray. Cray had been working on their own interconnects as well. And so, we were able to, basically put together the best from InfiniBand and the best from this Cray technology and form OmniPath. OmniPath is now the basis technology for Cornelis Networks.
Okay, tell us what your strategy is here. What's the problem you're really aiming at?
Right. I've been around a long time and seen things kind of evolving. It wasn't that long ago that applications could see significant speed ups all the time simply by waiting for the next processor to come out at a higher frequency. I think that world changed probably back in 2004, 2005 timeframe. And so now the best way to get performance improvements is to go parallel, right? And so, and of course, this has been well known in the high performance computing world for a long time. The problem that we're trying to solve in HPC and have been for a long time, usually around modeling and simulation applications, has been not how do we get more applications on a single server, but rather how do we get many servers working on the same problem at the same time. Okay. And so, that's, I guess, the fundamental problem that we're trying to solve is to improve parallel computing. which has had deep roots in modeling and simulation in the HPC world. But more recently, right, we're seeing it crop up in other really important markets. For example, artificial intelligence based on machine learning, right, especially the training algorithms. We see here is a dead ringer for parallelism, right? We have neural networks, okay, and we have maybe we have to try a lot of different specific architectures of the neural networks. We're not exactly sure which will be best for our problem. These neural networks. They need a lot of data to be run through them to be trained. Okay, they may even need to be tested with different hyperparameters to see what the learning rate should be or what the optimization algorithm should be. And so this turns into a gigantic parallel problem to come up with the best solution. Okay, and so artificial intelligence, data analytics, and modeling and simulation parallel algorithms is the problem we're trying to solve. So, I guess what had been happening for many years in high performance computing is that the problem set was modeling and simulation, typically based on message passing like MPI, and the nodes were typically, let's say, dual socket CPUs, Xeons or EPICs from AMD. But that also changed given all the interest in parallel computing. Now we see the need for AI. Okay, so much bigger data sets. Frameworks like TensorFlow and PyTorch, Caffe2 all have to be integrated in. We see the need for different programming models. Some of our big customers in the U.S. government care a lot about PGAS, for example. There's so much data being thrown off that now user space, object storage systems have come to the forefront. And then to try to drive all of the performance, we're seeing an evolution in the nodes as well. It's not just dual socket CPUs anymore, but now they're often surrounded by accelerators such as GPUs. Okay, and so in order to make all that work well together, a brand new software infrastructure has been defined. Okay, and that's how we're going after the problem set.
So it's a growing problem of growing complexity. So why choose Cornelis Networks? What do you all do differently or better?
No, great question. Thanks for that. So what's going on here, right, is we're seeing this brave new world emerge now, where the requirements are very different than they were 5 years ago. And so in order to meet the requirements, not just of traditional modeling and simulation, but AI, object storage systems, and so on. And so we started about 5 or 6 years ago, working with the Open Fabrics Alliance on defining a next generation software infrastructure that would not only meet the requirements we have today, but actually anticipate what was going to be needed in the future. Okay, and so there was something called the Open Fabrics Interfaces Working Group that was established. We spent a year trying to figure out, what was really going to be needed for the next generation of infrastructure. Pulled all sorts of groups from all different application environments, pulled all the requirements together, and that eventually produced something called the Open Fabrics Interfaces. And the first library implementation of that is called the Fabrics. Okay. And what's great about this is it's a coherent framework that allows you to run MPI. It allows you to run PGAS type applications using SHMEM and things like Chapel. It also integrates in Intel's new object storage system called DAOS. And it gives us the ability to actually put in GPU support, but portable GPU support. Obviously, NVIDIA's got a fantastic product line, a very popular product line today, but AMD has a great product line with the Radeon GPUs. Intel's entering the market as well. They've gone public with their Ponte Vecchio plans. And so it's important to be able to have one software infrastructure that can support choice in all these different areas. And so we have optimized our hardware, and now we've moved our software to this new Open Fabrics Interfaces capability. And so the product line that we have been selling based on technologies that we inherited from Intel, we called OmniPath. We're moving the software infrastructure up, and now the new product line will be called OmniPath Express. And that's just a software upgrade. And then the next step after that will, of course, be our speeds and feeds upgrade that also includes additional acceleration. Okay, so that's on the performance side, but we found that our customers care about two things, right? They care about performance, and they care a lot about price performance. Okay, and so the second part here is not just giving fantastic performance, but how do we make sure that the cost structure is as low as possible? And there's implementation decisions that have to be made. Of course, you have to use ASICs in this market, okay? Otherwise, your cost structure would be way out of whack. So you start there, and our competition uses ASICs as well. However, there are different implementation schemes that can dramatically drive up or drive down your cost structure. And so, for example, you want to make sure that you are, number one, focused on managing signal integrity in a cost-effective way. As these line speeds continue to go up, the cost of making sure that these signals can reach their destination can go up dramatically if you're not very smart about how you manage your signal integrity. The second thing is around cabling, okay? And so you could go into a path where you need exotic high-density cables that are extremely expensive, or you can be smart about it and make sure that you keep your cabling costs as low as possible. Finally, it's all about managing the thermals as well, okay? If you pick, the long radix switch, for example, with too high of a density, that then drives you into high density connectors, that can then drive you into liquid cooling only solutions, and all of these things can just drive up your cost dramatically. So it's really important to have the right balance, not just in the performance equation, but also in the cost equation, because honestly, in our market, there's really two first order requirements. Performance, number one, price performance right behind it.
So now looking ahead, can you give us a quick preview of what your roadmap looks like coming up?
Yes, exactly. So, where we are today, right, we inherited a great set of capabilities that we were able to acquire from Intel. That's our OmniPath, and that's what's in the market today. I can tell you that we continue to benchmark against competition and are doing extremely well with that product line. But we're really excited about what we're coming out with very early next year. And that's what I referred to earlier as OmniPath Express. So I guess we were kind of fortunate that our hardware infrastructure was built extremely well back in the day to be able to support OmniPath Express, the OFI implementation. And so we're coming out with that early next year. And I can tell you we're seeing dramatic improvements in latency, even more dramatic improvements in our message rate. Okay, and those are the two, I think, most important parameters for most HPC applications. We're also seeing much improved capability for overlap. Okay, so overlap is another really important one. We have to minimize our software footprint. So that means CPU occupancy. It means making sure that we don't pollute the caches or eject addresses out of the transitional side buffers, things like that. Okay, so very excited about the performance improvements we're seeing there. Then a little bit longer term, I'm not going to give you the exact dates yet, but we're also working on our next generation bandwidth improvements. Okay, the next big transition that we see on the horizon is moving from signal lanes running at 25 gig NRZ, they call it, to 100 gig running 50 gig PAM4 signaling. Okay, and that's our next generation solution that we're working on right now. You think of it a little bit more than a year from now.
Okay, well, fascinating stuff. Thanks very much, Phil, and wishing you a great SC21.
Thanks, Doug. I very much appreciate the opportunity to speak with you today.
Okay, thank you.